Hi, my name is Philip Gresham, and this is my Net-270 project presentation. So to start here, we have the Acme Corporation's three-tier architecture network here. It's a partial mesh. We have the core layer, the distribution layer, and then the access layer. And I say partial mesh because if these were connected, it would in fact be a full mesh. But as they are not, it is partial. So we have up here, this is all layer 3, layer 2 and 3, and then layer 2. So let's go ahead and just jump in with layer 2. Let's go into access 1 here. And let's talk about the way that these are connecting up to the distribution layer. So log in there. Now, each of these is a bundled and aggregated channel. And they use LACP, so show ether channel summary. And we can see here this port channels, so PO1. What this means is that these two lines here, ETH00 and ETH01, are seen by both of these switches as a single line called port 1, PO1. And again, these next two are PO2, PO3, and then it actually is PO4, 5, 6, and then 7, 8, and 9 across here. So we can see that they're also all up at the moment. They're not being blocked. And that is because of spanning tree, the root for each of these VLANs, VLAN 10 is voice, VLAN 20 video, and then VLAN 30 is data. To keep a loop from happening where, say, this one would be talking to this, to DS1 here, and then down to here, and then back up here, if these are two open, we have the root bridge. So DS1 here shows the main routes for VLAN 10. So if we go show spanning tree, VLAN 10, we should see PO1. Yep. Port channel 1 comes up as the root bridge, the root port, I should say, the port that connects towards the root bridge. The other two being designated, so they show to the other ones. VLAN 20 then is going to have, here we go, PO2, so pointing towards the root bridge for that, and we did this right. VLAN 30, yep, is going to be on PO3. So let's go ahead and follow VLAN 10 up to the next layer here. And in the distribution tier of the network, the high availability is attained by allowing these three switches to either act as a virtual gateway together, or in the case of DS2 here, to act as let's make this a little easier to see. DS2 acts as the gateway load balancing active. We'll get into that in a second. Let's start with DS1 though. This is high availability. This allows failover if, for instance, one of the uplink ports, these uplink ports can all be utilized. But we have control over it. It's not just random. So DS1 is using HSRP, and what that is, the hot standby router protocol is a Cisco proprietary protocol that allows for all the traffic to use a single virtual gateway and virtual MAC. So let's go show standby. Let's make that a little easier. Let's go show standby brief. Much easier to read. So we can see here, this is VLAN. This is the interface that the HSRP is on, is VLAN 10. This is group 10. The priority for this particular distribution switch, DS1, is 110. Preemption, so the ability to, if something were to happen to one of these switches, the if the switch goes offline and then comes back online, it forces everyone else it forces the election of the other switches to see who gets to be the active speaker. You can see in this case right now, DS1 is the active speaker. It's local. The standby, the next one down, is 10.2, which is DS2 here. And the virtual IP they're using is 10.254. So the reason this is important with the priority and the preemption is that right now all three of the switches are set up to track the state of their uplink ports. And let's go ahead and let's show track. If we go in here, we can see there's a tracked list, 10, 20, and 30. This actually goes for each of the three different protocols that's being used for each of the three switches. And track 1, so the first track 1 is the line protocol, whether it's up or down on E32. So if we go back here, 3.2, and the second one is E3.3. Hide those again. And what we're tracking is for 10 here, we have the track 10 lists the Boolean and, so if both are up, and so up and up is up and down is down. So that means is let's go show run section VLAN 10. With this track for standby for HSRP, standby 10, it tracks this 10, the protocol for both of them, and it decrements by 10 the priority if one or both of the links go down. And what that means is, let's just take a link down. Enter SE3/2. Whoop. Sure that's on there. Let's go back over here real quick. Oh, it's because it's ETH3/2. That would definitely change it. I'm already mentally in one of the routers right now. So enter E3/2. Let's go and shut. We should see, okay, OSPF got mad at us, and we'll talk about that in a second. But the VLAN changed from active to speak here. And do show standby brief will give us that now we're in the listening state with the active speaker being the 72.16.10.2. Standby has actually become this one down here because we're now higher up. And the priorities descend 110, 105, 100. And if we no shut again, it will force the election. Come up and we can see that the priority is back to 110 and we are the active local again. And OSPF has come back up. DS1 and DS3 are fairly similar, so we'll just glance over DS3 real quick. It is running this is the main speaker for VLAN 30. It is using VRRP, which is the open standard version. And we can see again priority 110. Preemption is yes, the state is master address, the group address. One thing worth noting is that, when I close that, show run, CVRP. Authentication with this is with text. So the authentication phrase, this allows these switches to make sure that who is saying that they have the higher priority is in fact the one who should have the higher priority, and it isn't a spoofed switch or somebody even with a laptop just trying to either divert traffic, change traffic patterns, or take down the whole network. DS1, let's go back to, let's get out of that. Show run, VLAN 10. You can see here, this actually is a hashed. It's slightly more secure. It's MD5, and this is the key string that all three of the switches have to know to be in standby group 10. Close out of that. And DS3 also has a very similar track where this is the first, so with this one, this was the first, this is the second one, and this is the third in a failover. This is the first. With the RRP, this is the first, this is the second, this is the third. And then with GLBP, which we'll get into here, you can see all the syslog messages about the state change from what we just did. This is the first, this is the second, this is the third. So, log in here, show GLBP brief. And the difference with GLBP is that all three of them, all three switches are still forwarding traffic, with the difference being that the active speaker is talking to these two. So when there's an ARP request, DS2 actually replies. And in the case that DS2 has a link go down, whoop, that's not good. In the case that DS2 has a link go down, DS3 automatically takes over, and then DS1 would take over after that. The tracks on this too, show run SE VLAN 20. The tracks on this then are waiting. And what that means is the ratio of traffic that is going to be sent to this switch in the case of a failure of either or both of these links. It's still Boolean and. And what it'll do is if this switch goes down, it decrements from 30, it's going to decrement down to 10, and these two will take up the bulk of the traffic. So, rather than shake them up, we're going to go ahead and just move up to, let's move up to OSPF. We'll move over to router 1 here for this. Maximize this because this is big. Show IP route OSPF. I say this is big is this is the, so because this is an area border router, this is going to see everything from everyone. It's also going to have and this is why I also wanted to go over to this one, show you real quick. If we go into DS1, show IP, go back here, OSPF, we'll see that we have these 99.0/24. Let's see, 10.0/8, the default routes, and these are all, this is learned by OSPF. And it's a much shorter list. Why I want to go into R1 is we have these null routes here. This is because this router is summarizing into the different areas of OSPF. Come back over here. This is area 0, this is area 20 over here. It has a leg in, this one's a tunnel leg, but it has a leg in area 0 and area 20. And so it has these null routes installed that are summaries. That's because with the VLANs, this is the 172.16.10.0, this is .20.0, and .30.0. So in summarizing it, we end up with 172.16.0.0/16. So with that being, this being the mask, and these being open. Because we only have 10, 20, and 30, if, for instance, someone were to say, well, I want a route to go to this router and say, well, I want a route to 40.0. since the router doesn't have that, instead of forwarding it out and just sending it into a loop, it would go to null 0. And this null 0 is, it drops the packet. So show run OSPF. We can see here, this is area 0 range area, and this is area 0's range. Area 20 range, this is the 192.168.0, and 4. If they wanted .5, that would be, again, not available. So, yes, we're in R1 still. So let's go ahead. Let's bump this down a little bit so we can see our topology. Minimize it. So OSPF is going to give us all of our interior stuff, but if we are going to want exterior routes, we are going to use Border Gateway Protocol, the internet standard for dynamic routing. And so what we have is going to be this is Autonomous System 6500. This is, I have it only ovaled over these two routers because they're the ones who are actually broadcasting as Autonomous System 6500. This whole thing would be AS 6500. This system is 7000, 2200 is level 3, and then Comcast is 3000. Let's go in here. Let's look at that BGP table. And that is a very short table. So the only route that R1 is learning currently from BGP is the gateway of last resort, 209.65.200.166, which is this. And that is a good thing because simultaneously, and we'll jump into R2 and show that as well. Show IP route, BGP. It's also only learning this one default route from Comcast, this 150.50.100.70, which is this interface on Comcast. Now, that is what we are going to want to have happen because if we did not, the BGP show runs as the OSPF. Whoops. Default information originate is in here. And this would end up with, we could end up with the whole routing table of the internet on R1 and R2 if we did not have some controls in place. Likewise, those routes could then be propagated across the rest of the network with this router saying, well, I know level 3's entire routing database. Would you like to see it? And that could be bad. Likewise, if we had a control, and let me just show this again. Well, it's already up here. Because these two routers are both running BGP, there is another route here, the show run section BGP. You can actually see that we have neighbor 10.0.0.2 in here. That's R2. The reason we don't see that route installed in here is because it's connected, which means that it has a metric of 0 compared to the 200 of BGP. And so let's see. Let's get into, though, how we are not getting everything from the internet in here. And that is this prefix list, default in. This only allows the routes that are default routes to be installed. And we'll go show run. Let's see. Oop, I copied that. We have a prefix list here. This is sequence 5 permit and 0.0.0.0/0, which this is going to mean that it can only say, well, I'm the default route for everything, and not I'm the default route for everything, and also I have a 24.0.0 something that I would like you to know that I have. Which keeps the list short. It's really all we need to know is that the internet and everything internet-wise is out that way. The other thing that's here and is on both of them is this local only route map, which this route map, show run, see, matches this AS path. It's an autonomous system path here. This is going to be permit and this regular expression, which is going to say, with the local only out, we are only going to show things that we locally learned. So even though R1 is aware of the connected route to Comcast from this one, we're not going to transmit. We're not going to say, well, I also know this. I know this other route. And in that way, we do not end up with what's called the transit route, where AT&T would be able to send data to Comcast through this AT&T to R1, R1 to R2, and R2 back out to Comcast. It has to go through level 3 because it doesn't see this transit route here, which could also very potentially wreck traffic flow and overload this entire system. Next, let's move up to AT&T here with what they're doing to make sure that our private address space, our RFC 1918 spaces, are not being broadcast to everybody. So show run SE BGP. We'll see here with AT&T and all of the telecom has this prefix list on it. We have prefix list RFC 1918N. We have show run SE. We'll see that this denies the installing the N, so installing into our routing table anything that has a 10.0.0.0, 172.16, 192.168, and then permitting everything else to be installed. So that show proute BGP. You can see that 174 is about as close to anything as we get, but that none of the private address space from any of the routers are going to get in there. So now let's close that out. So now let's talk about how Acme gets traffic to the internet if those addresses are going to be blocked. If those addresses, the address space from RFC 1918 is blocked. And that is NAT. So let's jump into, we've played with R1 enough. Let's jump into router 2. Show IP NAT translations. And so network address translation, this means that we can put a global address onto a local address. And this maps 1-to-1. We also actually have show IP NAT stat. We also have an address pool that is 65 and 66, which is allotted to do what is called port address translation, PAT, for all other traffic that isn't these 6 servers, or in this case, these 1, 2, 3 servers. This one, and this one go out R1. And the reason for that, and the reason that we don't just have these going out port address translation 2 is that these ports, the ports that are assigned. So if let's get a good. I can't remember what Comcast is. Let's show IP. That should make me log in. There it is. Show IP, enter brief. going to try to hit this address. So let's jump into DS3 here. And let's ping that address. We've got some success here. Jump over to R2, show IP NAT trans. Actually, let's show IP NAT stat. And it looks like I actually have show IP NAT trans. There it is. Okay, so it actually went through R1. And you can see our inside local that was translated is this one out to the outside global. And 161 and 162 are the, let's just show IP NAT trans. Whoop. IP NAT stat, I meant to say. Our pool is 161 and 162 here. And we can see we had an allocated, so 50% now. Show run SE NAT. And we have, it's a inside the source list is going to be the inside addresses, and then overload. This means it's going to be port address translation. And we're overloaded at the moment. It tends to get a little, GNS3 does tend to get a little buggy, I've learned with NAT, especially when it is given quite a few pings. So we're going to play nice today. Let's go over the data server here. This is 30.12. So if we'll remember from R2 here, show IP NAT trans. 30.12 is going to be 100.69. This one here. And I've lost what I had, so we're going to go back to DS3 and get that 64.100.166 from Comcast. Let's go ahead and ping Comcast. And now with this one, because it's a static translation, I can tell you where it's going to come out. You can see here 100.69, and this is every single one of those pings loaded up a different port, but it is all going to be that same IP address. And if we go back to Comcast, let's just steal that address. Whoop. Ping. Got a success rate of 100. Let's do it again. Again, just to really load that up like I said I wouldn't. And here we can see 0, 1, and 2. This is every one of the translations that's been done. So that is the NAT that is on both of these. The next real big thing to talk about here is, so how would we get, if this, and we already know that this is an OSPF area that is somehow communicating with this, but how are we going to be able to get secure traffic across the network? And the answer is tunnels. So let's go here and let's go look at a path from R1 again. Let's go back to R1. Let's make this fun. See if this will have too much latency here. SSH. Let's go into the management address for R1. It's Acme Corporation, so Anvils and Wile E. Coyote. And let's trace route to 192.168.99.10, the management address on recovery DC. Oh, 1992 is not even close to 255. I will see that it goes through this 10.0.0.6 and is immediately there. And that is because, show IP enter brief, include tunnel. And we have this tunnel here, 10.0.0.5 to 0.0.6, which is actually bringing the traffic through a secure tunnel. It's encapsulating the traffic that goes from R1 over to the recovery DC. And go ahead and log out here because there is a little bit of latency to it. And if I ever try to get back into admin remote, I'll be very confused when it says R1. So first thing, let's go ahead and look at here. Let's go for show run SE crypto SE tunnel. Let's just get everything out here in the open. So here we can see that the encryption is set up for the key exchange up here. So we have a policy that's going to do group 16. This is 4096-bit Diffie-Hellman key exchange. The key, because again, let's go over to show IP enter brief, include up. 174.111.70.81 is the public address for the remote domain controller. And see over here we have a key for it that if it knows this CCNP 270, and in a real, were Acme a real production network, this would be a randomly generated very, very long string of a password. I use CCNP 270 here just to make this less gibberish in explaining. But the address is here, and it has a lifetime. This key can only exist for an hour, 3,600 seconds. Has to be pre-shared. It's hashed in 512 in SHA-512, and the encryption is going to be AES-256 for this policy. Down here we can see I actually originally had AES and SHA-256 as the ESP, the encapsulating security payload protection. Yes. For the payloads that go through here, the packets. I, however, have moved it up to AES with SHA-512, and that is because GNS3, the computer that I'm running this on, is a 64-bit processor, and SHA-512 works a little bit faster on 64 bits because it is a 64-bit word instead of the 32-bit word, so it gets to use the entire processor to get through this 512, while still giving us essentially double the amount of protection of encryption that a 256, that SHA-256 would. We have mode tunnel, so these are VTIs. And the transform set is going to be set for this VPN1. Let's go to show run SE. For some reason, it did not tunnel. There we go. I'm going to focus on tunnel 1. I've adjusted down the maximum transmission unit to going to be 1400 to account for the overhead from this. This address, 10.0.0.5, this is tunnel 1. The remote address is going to be the 174. The tunnel destination goes to this one, and it's actually mapped to 10.0.0.6 over here. And it uses this profile VPN1, which means it's going to use this transform set, which means it's going to use this ESP here. So other things to talk about here, let's go show crypto session. We can see here that the session is open between the two of them, that everything is allowed to flow through. And if we go to show crypto IPsec SA and include encrypt and decrypt because we don't want to have to dig through everything. You can see that we've had several thousand, and this I left the network open for about an hour before this to let everything kind of calm down. A lot of times with GNS3, again, when this network opens up, the flood of hellos from both BGP and OSPF tends to crash R1 and R2, DS1, DS2, DS3, and then AS1, AS2, and AS3 with the port channels tends to get a little buggy as well. So I've left it open for a while. We can see several thousand packets, mostly hellos, have been OSPF neighbor hellos have been sent across this tunnel. So I can say all day that this is encapsulating, but since we really can't just pull one of these wires out, look down the end of it, and especially since it's virtual, we can't pull a wire out, look down the end of it, and just see that it's encrypted. We can do the next best thing, though, and we can do a capture here. Start up Wireshark. We can prove. You can remind me on that later. You can already see the ESP stuff coming up. There's a CDP. Whoops, didn't log into AT&T there. Let's ping recovery DC. Show. And so let's ping the recovery DC across the open internet here, the non-trafficked internet from AT&T, to simulate what it would look like if somebody, and I'm going to put this over here, open up Wireshark. And because we have all this internet traffic going here, let's go ahead and ip.proto equals 1, ICMP, ping. And there we go. We immediately have that these are all ICMP protocol between the 12.44.33.6, which is this exit interface on AT&T, to the recovery DC. And it's all out in the open. We can see that this is ICMP. Don't even have to guess. Let's close out AT&T. Let's go over to R1 and ping. Let's do the same thing here. We can still see that we're getting public. And remember, we were at 97 here. Is going to be our last one that happened. Let's go ahead now and ping, though, the management address of recovery DC, 68.99.10. Whoops. Let's see what's going on here. And 99.10 is there. And this might be that tunnel has expired a little. Tunnel 1. So let's see if we can ping 10.0.0.6. Oh, that would do it too. 192.169. We don't have a .169 in here. So let's go back over here, and we can actually see already the set of echoes, but let's, just for laughs, can see again that 97, still at 97. We are not seeing any ICMP traffic. Trace, whoop, almost did it again. .10. And our 10.0.0.6 is, that's the data server. Looks like we closed it. Let's just exclude down. And 99.10 here, 10.0.0.6 is the other tunnel. Now, if we change this to protocol equals 50 or IPsec, we can see a lot of ESP traffic going on here. Let's go ahead and run this again. And there we go. I had a real quick little jump. So let's catch one before it goes away here. Let's inspect that. So this would be 742.209. This would be an echo reply. And we can see that it shows it as an encapsulating security payload. And there is nothing in here to show us that this would be an ICMP packet. So it looks like it's working. If we were to do this on a real production network, another way to do this would be to stand up a TFTP, a trivial file transfer protocol server. Let's quit. And try running traffic from one of these. So sending, say, a text file, a clear text file, up from the video server to recovery DC and uploading to an FTP, which in a backup situation would usually be secure, so SFTP. But if we use TFTP, it would transmit in the open and be able to see whether we can find in any of those payloads any sort of evidence of plain text. So let's go ahead and talk about Acme's plans for the future. So right now, this company, this is a pretty nice redundant network, has a lot of fail-safes and a good amount of security. But in a real world setting, this would be probably quite a bit less likely, or quite a bit less than they would likely need. So it can be argued that this BGP filter, this is going to shield a lot of our traffic from being able to be, our interior IP addresses from being accessible from the greater internet. But we can't really, this is AT&T and Comcast, we can't really guarantee that filter is even there between our two autonomous systems. So with that out of our control, really we're just left with the NAT, which is the PAT stuff, not even NAT, the port address translation, which is going to shield our general users from being able to be essentially hacked, but also show access lists. The only other real thing that we have right now is this remote management extended access list that permits admin remote while denying everybody else TCP to port 22, which would be an SSH session, while permitting everything else. We can already see that there have been 3,180 matches for permit any in and out. So I'm going to close that out. One of the big things that Acme would want to do, go ahead and switch over to Paint here, would be to add an application security appliance, an ASA firewall. Let's make this red because of fire. Here and here in line. And this would be more effective, will let us add more effective policies, would also let us have more granular control over what is going into and out of the network and monitor traffic flows for malicious activity. Another benefit of having ASA firewalls is that quite a few of them, the Firepower firewalls by Cisco, for instance, we're going to have DMVPN or even Flex VPN capabilities that are going to be more secure than the VTI IPsec tunnels that we're currently using to get traffic across the WAN. Another Another thing that would be very useful to have here would be a TACACS server to limit console access. By that I mean because right now, if I hit enter and I log in, all I need to know is admin and the password for admin, and I'm in. Even if I had heavy syslogging going, it would show that username admin logged in and changed things, either for better or for worse. And this could mean an accidental or even malicious login to the network. It could also mean a malicious login even to one of the servers through one of the KVM. There's KVM logins, the virtual machine logins. And having a TACACS server would allow us to have identity management, would allow us to be able to say, I know who has logged into this and who changed this code because it's logged on both the server and then also in the device. It would allow for individuals to have their own username and password and not just this shared admin password that we all have. Now, another thing that would be very useful for Acme, should they decide to move and expand to multiple sites, I would very highly recommend something like a DNA center. And using a DNAC server to convert this to a software-defined network would allow more centralized control of the traffic flows across the network fabric. DNA would also allow Acme to manage multiple sites over an SD-WAN connection. And that would allow them to make everything seem as a single fabric domain and allow one IT team to manage everything centrally. It would also really negate the need for a lot of the failover, the load balancing and failover, because DNAC would be able to do that. In addition, also, if they decided that they wanted wireless access, they would be able to use wireless LAN control, WLCs, wireless LAN controllers, connected to the DNAC, which would allow for them to visually see heat maps, to see even down to the granularity of who logged in with what device, physically where in the building in Acme Corporation or in any of its branch offices. So thank you so much for your time. I hope you enjoyed this presentation, and my name is Phil Gresham, and thank you.